Welcome back, everyone. Today I'll be continuing to discuss some concepts of group theory in the context of the Rubik's Cube. A very important concept in group theory is the concept of subgroups. So a subgroup is just a subset of a group that itself forms a group. And they're important because they can be thought of as kind of being the building blocks of the group itself. The binary operation of a subgroup is always the same as that of the parent group. And for those of you who have some experience with object-oriented programming, you might say that the subgroup inherits its binary operation. In fact, any subset of a group actually also inherits associativity. So to show that something is a subgroup, you only have to check inverses, the identity, and then closure. When we talk about groups on their own, a lot of the time the closure property is kind of self-evident, but for subgroups it's especially important. For example, we can put a group structure on the set which just has the numbers 0 and 1 by using addition modulo 2, and that's closed because 1 plus 1 equals 2, which is the same as 0 when we're doing addition mod 2. However, if we take this as a subset of the integers mod 3, then it's not closed because you get 1 plus 1 equals 2, which is not equal to 0 because addition modulo 3 makes 3 equal to 0. We talked about generators last time, and the easiest way to find a subgroup is to omit some of the generators. So instead of using terms of all the different possible sides of the cube, we could just restrict ourselves to using only a couple of them, say the right side and the upper side. Now, an important concept is what's called the order of a subgroup, which is simply the number of distinct positions we can get to using the generators that we chose for our subgroup. So, for example, if my generator is the move R2, here I get one permutation. If I repeat it again, then we get back to solved. So there's only two elements in that subgroup generated by R2. So the order of that group is 2. And if we just repeat one sequence over and over, then we also get the concept of the order of an element, which is the order of the subgroup generated by that element. In fact, you can generate a subgroup using any sequence of moves. So let's say I want to do R and U, so that's my sequence, and I'll repeat that over and over again. And that will generate a subgroup. And there's actually, in this case, there's actually a lot of possible permutations that we can get by repeating that sequence over and over. So we found a subgroup of order 2, which is generated by R2. And we can also, instead of doing R2, we could do R, and you'll see that there are 4 different permutations in that subgroup. But what about a subgroup of order 3? Well, one idea would be if we could find a way to twist just one corner, then if we had an algorithm that could twist a corner like that, it would take 3 repetitions to go back to solved. Unfortunately, you can't just twist a single corner on the Rubik's Cube, which is for reasons that we'll get into later. But you can twist 2 corners at a time using this sequence. And so if you repeat that 3 times in a row, then you'll go back to solved. So that sequence generates a subgroup of order 3. Now it turns out that this subgroup of order 3 is essentially the same as the group of the integers mod 3. Essentially the same here means what's called an isomorphism. And what that is you have a map which renames the elements so that we have each element of the corner twist subgroup is assigned to exactly one of the elements in the integers mod 3, and every element in the integers mod 3 gets assigned by one of the elements in the corner twist subgroup. And it also satisfies this property, which I'll have on screen. But for our purposes, isomorphism just means a renaming of the elements that makes the group work in the same exact way. Some of you may have seen a viral video claiming that you can solve the Rubik's Cube just by repeating a short sequence over and over. This is false because you need more than one generator for the Rubik's Cube, but it does point to an interesting fact. If you repeat any sequence of moves over and over again, eventually it will cycle back to being solved after going through every permutation that is generated by that sequence. This is ultimately because the Rubik's Cube is a finite group, although it does have approximately 43 quintillion permutations, so finite doesn't necessarily mean small. In the future, I'll probably make a video explaining how to actually compute how many permutations there are. But if you're curious right now, there are some videos that other people have made on the topic. So the reason that any sequence of moves, when repeated enough, will cycle back to solve is because if it didn't, that would mean that it would generate infinitely many different permutations. And since the subgroup generated by that sequence is a subgroup of the Rubik's Cube group, that would mean that the Rubik's Cube group has infinitely many elements, which it doesn't. So we can't have any such sequence like that. Now you might wonder what possible orders of subgroups we can have, and the answer to that question comes from Lagrange's theorem. Lagrange's theorem says that the order of any subgroup is a factor of the order of the larger group. So for example, if the order of your group is prime, since the only numbers that divide a prime number are 1 and itself, the only proper subgroups we can have to have one element in them. You can actually show that the only subgroup in a group of prime order is the subgroup which is just the identity element. And the proof has to do with closure and a property which is unique to the identity. And if you're interested, I would definitely recommend trying to work that out yourself. So to apply Lagrange's theorem, you can factor the order of the Rubik's Cube group like this, which I think I'll put on screen here. And factored like this, we can see that 13 doesn't divide the approximately 43 quintillion different ways that we can scramble the Rubik's Cube. And so, by Lagrange's theorem, we can't have a subgroup of order 13.